Welcome back to the Explainer. We are diving right back into the Merg-E language specification. If you'll remember, we're doing a series of 6 explainers, each tackling 4 posts of the spec. Today is part 2, and we're zeroing in on parts 4, 5, 6, and 7. So if you're looking to decode the mechanics of modern language design, you are absolutely in the right place.
Just to set the stage here, we're right in the middle of an objective, bottom-up technical tour of Merg-E's core mechanics. We're not here to overhype it or declare it the ultimate programming paradigm. No, we just want to understand the strict mechanical constraints the compiler uses to manage authority and execution. So today, we're looking at the engineering choices behind execution control, lexical scoping, structural data, and immutability.
Okay, here's our technical roadmap for today. Section 1, locks and blockers. Section 2, semantic lexing. Section 3, DAGs and authority. Section 4, constraints as data. And Section 5, immutability and freezing. Let's dive in.
Section 1, locks and blockers, execution constraints. So right off the bat, Merg-E doesn't just leave the execution flow up to the runtime. It uses incredibly strict execution constraints as a foundational feature. We're talking about semantic locks, blockers, continuation points, and hazardous blockers. And these aren't just polite suggestions from the compiler, they are absolute structural boundaries. The runtime uses them to know exactly where execution can pause, resume, or lock. And what's absolutely crucial here is that these constraints dictate what other features are allowed to do. Like when we get to part 6 later, you'll see that inline lambdas are explicitly forbidden from using blockers. If you want pure compute without side effects, you literally cannot introduce a blocker.
Section 2, semantic lexing, single keyword design. Now what's really interesting here is how Merg-E handles its extreme minimalism. Because it uses a single keyword design, the lexer actually has to step up and do some seriously heavy lifting, stuff you'd normally expect a parser to handle. This semantic lexer dynamically tracks authority between execution contexts. It's managing authority propagation, implicit and explicit capturing, and even tree pruning. That means a token that works perfectly at one level of your program might be totally invalid deeper down, or maybe it's only reachable through a completely different identifier. The lexer is literally pruning and grafting the environment on the fly to resolve names and manage authority.
Section 3, DAGs and authority, directional acyclic graph.
Okay, so if the lexer is juggling all of this authority, how is it actually organizing it? Well, it uses a directional acyclic graph, or a DAG, to build a heavily restricted environment. Pretty much the entire language and all ambient authority is anchored straight to the scope root. It's kind of like a strictly pruned family tree. Authority and name resolution only ever flow downward. You can definitely create aliases, but to keep that DAG directional, an alias has to point strictly downward to a child. You absolutely cannot point an alias directly to another alias. Oh, and the single structural exception to this strict hierarchy? Operators.
Mechanically speaking, passing authority down the tree happens in a couple of steps. First, it kicks off with a use operation. Second, an explicit capture triggers deep copies of the non-static components, taking them from the parent's scope.export and dropping them into the child's scope.import. By deep copying instead of just referencing, the child context gets exactly the authority it was explicitly given, and not a drop more. It's a really smart way to silo execution environments for much better security.
And get this, it's not just some hidden compiler magic. As a developer, you have active user space tree control. You can use commands like prune, ent, which stands for graft, and alias. You can actually tear down your own ambient authority. Say you have full ambient authority at the app level, right? You can just prune I/O right out of it before passing it down. Boom! Now your lower level execution contexts can't ever touch the file system or the network because in their reality, that branch of the DAG literally doesn't exist anymore.
Section 4, constraints as data, replacing structs.
Merg takes a totally different approach to data structures, which brilliantly illustrates that minimalist philosophy we've been talking about. Instead of baking new data structures into the compiler, it just reuses that DAG concept. So where a traditional language hands you dictionaries, maps, or structs, Merg gives you unfrozen and shallow frozen DAGs. An unfrozen hand-built DAG takes the place of a dictionary or a map. Meanwhile, a shallow frozen DAG, which locks its structure completely in place, steps in to act as your struct.
But wait, what about collections? To replace lists and sets, the spec experimentally relies on just one single collection primitive, the data frame. By optimizing entirely around the data frame, the language elevates the Parquet data format into a first-class citizen.
This is highly intentional, built specifically for highly parallel, asynchronous processing environments where classic lists would normally just create massive performance bottlenecks.
So the crucial point is, if we're going to process all that data safely, inline lambdas have to be absolutely unconditionally strict. They have to be pure compute, meaning zero side effects. They cannot explicitly capture variables, they can't be defined as mutable, and they definitely cannot include any blockers, which ties right back to our first section today. Plus, all arguments are passed entirely by value. This absolute strictness is exactly what allows these inline lambdas to safely mimic classical return value patterns inside a highly parallel least authority environment.
Section 5. Immutability and freezing. Locking data down.
All right, so if we're replacing structs with DAGs and forcing pure compute, we obviously need a rock-solid way to lock our data down. The rules here are simple but deeply impactful. First up, constants are implicitly frozen. Unless you specifically flag a constant as sensitive, the compiler just assumes it holds no authority and freezes it right out of the gate. Second, we have shallow freezing. Like we touched on earlier, this is the exact mechanism developers use to finalize a custom DAG into a rigid, struct-like data container. It permanently locks the shape of the data, so you can safely pass it around the execution environment.
We've covered a huge amount of technical ground today, from semantic locks to data frames, and really seen how structural constraints are essentially the primary features of the Merg-E compiler. But looking at all these strict data rules and deeply frozen DAGs, you gotta wonder, how do these constraints actually impact capability patterns and attenuation when you're building real-world applications? Well, that exact question is going to be the sole focus of Part 3 in our 6-part explainer series. Thank you so much for hanging out with me today, and I'll catch you in the next one as we keep decoding the Merg-E spec.